It's an important definition, which fits the pattern for most of the math you've done in your math career. First, you learned about adding numbers, then you learned to subtract them, because adding and subtracting undo each other. You learned about squaring, and then you learned about square roots, because squaring and square roots undo each other. So we have learned how to take derivatives. We'll learn a little bit now, and then a lot second semester, about antiderivatives. An antiderivative is a function whose derivative is the function you started with. So a function capital F of x is an antiderivative of little f of x if capital F prime of x equals little f. If you can take the derivative of capital F and get little f. And that has to be true for every x in the domain. To find an antiderivative, we call antidifferentiation. So lots more about antiderivatives second semester, but we want to introduce this idea here, and we can find some simple ones. And this is, again, similar to what you did when you were younger. When you learned how to multiply, you probably had to memorize a bunch of times tables facts. And then your introduction to division was thinking about a multiplication fact that you knew and like filling in the missing piece. So you knew 5 times 3 was 15. So later when you first learned about division and you explored 15 divided by 3, you thought of that one multiplication problem that you already knew, and you knew the missing number was 3. So, or 5, whichever I said. So that's going to be pretty much as we're going to do with antiderivatives for now. We're going to find antiderivatives by thinking through this catalog of derivatives we already know and see if we can think of one that fits. So on your paper, find any antiderivative of f of x equals sine x. So that's interesting, find any antiderivative. It turns out that there is more than one. In fact, there are infinitely many functions that I could take the derivative of to get sine of x as the answer. So the first one I think about, I think maybe it might be cosine. I'm like kind of checking through this catalog. I'm like thinking through a catalog of functions that I know how to take the derivative of, and I'm looking for one whose answer is sine of x. Well, so I think of cosine, but the derivative of cosine is negative sine. So what function can I make so that its derivative is regular sine? So I'm going to choose, whoops, it was supposed to be the pen. So I have to think of a kind of like a little tweak factor of negative 1 so that this works. So I'm going to say capital F of x is, it can't be cosine of x because the derivative of cosine of x would be negative sine. So I'm going to start with the function negative cosine of x. And I can check my answer to an antidifferentiation problem by taking the derivative. So if I take the derivative of negative cosine of x, do I get sine of x? I sure do. So I have found an antiderivative of sine of x. Well, we have this other rule too, which is that to take the derivative of a constant, I get 0. So that tells me that I could have picked any number of functions. I could have said the antiderivative is negative cosine of x. That's poor planning. Negative cosine of x plus 7, or negative cosine of x plus 9, or negative cosine of x minus 5.5. So this is a good answer. It's an antiderivative. I could have another one. I could have said f of x is negative cosine of x plus 3. Could have said it was negative cosine of x plus 9, negative cosine of x minus 8.3. So the thing that's different about all the possible answers is the constant at the end. So instead of saying, here's a function that's an antiderivative, I could also write an expression, a formula, a function for all the possible answers. So all the possible antiderivatives of sine of x have this form. F of x is negative cosine of x plus a constant. And we've settled sort of on this capital C is what you'll typically see people use for that number that's going to get added at the end. I don't have enough information yet to know what that number was, but I am certain that no matter what that number is, that c is, if I take the derivative, I'm going to get, in this case, sine of x, because the derivative of that constant will definitely be 0. So this is the piece that we need if we're going to answer the next question. What if I want to find not just any antiderivative of sine of x, but the antiderivative sine of x, which also has f of pi equal to 7? So that's what I'm going to start with. I'll start with this general form, this negative cosine of x plus c, acknowledging that there could have been a number there. And I'm going to try to figure out what c is to make this statement true. So I'm going to find f of pi. That means I'm going to replace x with pi, negative cosine of pi, plus some constant. And I want that whole expression to equal 7. Well, the cosine of pi is negative 1. So negative cosine of pi is negative negative 1, which is positive 1, plus c equals 7. That tells me that c must equal 6. And now I can write my final answer. The answer for this example, I would say, f of x is negative cosine of x plus 6. All right, so this one is in your textbook, page 202, number 15. I have a function f of x. I want to find where f is increasing, where f is decreasing, and any relative extrema. So these all require my finding f prime of x. Oops. So that's my first step. I'm going to find f prime of x. See why we practice so much in chapter 3? That should be 5 minus 2x. And I'm interested to know where f is increasing or decreasing, which means I'm interested to know where f prime of x is positive or negative. So I like to make, this is called a sign chart, S-I-G-N chart. I'm going to figure out where f prime of x equals 0. And that's true where 2x equals 5 or where x equals 5 halves. I'm going to mark that on the number line. I could test a point from each section. It's probably worth doing. So I'm going to test 0 when x is 0. 5 minus 2x is 5, which is positive. If I'm going to test a number bigger than 5 halves, I don't know, maybe I'll test x equals 4. 5 minus 2 times 4, 5 minus 8 is negative. So I notice that I'm answering part A last. I'm okay with that. So part B, I would say f is increasing on, okay, at this point you could use interval notation or you can use inequalities notation, but we have to find a way to say increasing. I'm looking for the place where f prime is, if you make a sign chart, try to make a label so you know which function you were testing. I'm interested to know where f prime was positive, and that's everything less than 5 halves. So I'm going to say x is less than 5 halves. Or I could have said negative infinity to 5 halves. Don't have to give both. I'm giving both. You would be expected to recognize both on the AP test. Because f prime of x is positive on that interval. My answer to C, f is decreasing on, we say on an interval or at a point, but here I'm talking about an interval. It's a whole section of the number line that we're talking about. F is decreasing on, I'll write it in red, you can either say x is greater than 5 halves, or you could say 5 halves to positive infinity. Both good answers. One is using inequality notation, one is using interval notation. And then I'll finish the answer because f prime of x is negative on that interval. So this one was pretty easy, less complicated than the last example we did where we made a sign chart because I only had 1 0. So there are only two places on the two sections of the number line to test from. So we'll do lots more practice with both kinds. So now it's time to go back and answer question A. I want to know where there are any relative extrema of f of x. So we're going to reason through this one. It's actually a big topic in 4.3. But think about this. I have a function f prime. I have a function f, and I know that it increases until I get to x equals 5 halves. And then after x equals 5 halves, it decreases. So that means f goes uphill, 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 until the time when x equals 5 halves. And then it starts to come downhill, 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 downhill. So I could have drawn that graph, higher up or lower down. But the thing that we know is at the place where x equals 5 halves, the graph changed from going uphill to coming downhill. So no matter how you draw that, and we don't have quite enough information to know exactly how high we should have made it, but no matter how we draw that, we're going to end up with a top of a hill at the place where x equals 5 halves. So here, f of x has a relative maximum at x equals 5 halves because f changes from increasing to decreasing at 5 halves, or because f prime changes from positive to negative. They'd both be good justifications. We're going to talk about justifying that very formally in 4.3. So this is just to kind of get you a little preview of what's coming.